Next lecture is left ventricular mechanics. This is a very important conceptual discussion. It's going to give us the bridge to do a whole lot of things in some other discussions. Let's talk about the left ventricle. That's what we're going to focus on in the performance measurements of the left ventricle. That's the pumping chamber of the heart. And if you have disease of the left ventricle, we call that cardiomyopathy. And it's actually been simplified recently, and the nomenclature for cardiomyopathy is much simpler than it used to be. So let's kind of go through a few things. If you have a ventricle, normal shape and normal thickness, you have two possibilities really. You can get a very enlarged ventricle with thin walls, in which case your ventricle would look like this. That would be called a dilated cardiomyopathy. Very descriptive. It's a dilated heart, larger than normal. Or you can get what they call a hypertrophic heart or hypertrophic cardiomyopathy, which has about the same size but is much thicker. The walls are much thicker. As it turns out, you can either go from a normal heart to a dilated heart, which is kind of an end-stage heart, or you can get a hypertrophic heart, and if left untreated for long enough, it will eventually head that direction. So sometimes when you see a final heart like this, you don't know if it's been a hypertrophic heart or not. If you have this heart versus this heart, which do these hearts have increased muscle mass? What do you think about this heart? Increased grams of muscle compared to this heart. This heart compared to normal. Yeah, really, really thick heart. A lot of muscle cells there, so it's thicker than normal. What about this heart? Does it have an increased muscle mass? Turns out it does. It's one of those optical illusions. It's like the tall, skinny glass versus. It's so big that it looks thin, but overall it still has more muscle mass. So both of these hearts have more muscle mass. This one has the most. This one has the second most. This heart this is not good grammar, but this is what I say. This heart is more bigger than it is thicker, and this heart is more thicker than it is bigger, but they're both bigger and they're both thicker than normal. Okay? So that's hypertrophic cardiomyopathy. That is dilated cardiomyopathy. The hypertrophic cardiomyopathies have a subset, and that's called hypertrophic obstructive cardiomyopathy. If you have a blockage of outflow in the left ventricular outflow tract and obstruction, then it's a hypertrophic cardiomyopathy with obstruction, or a hypertrophic obstructive cardiomyopathy, which we call HOCM. The old word for that used to be IHSS, idiopathic hypertrophic subaortic stenosis. That's a tough word. This one makes a whole lot more sense because it puts us right into our nomenclature of what we call cardiomyopathies. If you remember back to the echo lecture, we talked about this is what the left ventricle looks like on the echo and the peristernal long axis. We'll draw this again. Here's the left ventricle, here's the aorta, here's the left atrium, aortic valve, mitral valve. What are some of the features? Why do you get an obstruction to outflow with hypertrophic obstructive cardiomyopathy? One component of this is what they call ASH. These are all great board questions. Asymmetrical septal hypertrophy. These are really good initials. They're pretty easy to remember. What that is that's a disarray of muscle fibers, and so the heart muscle gets thick primarily in one location. That's the septum. So what you get is you get a muscle that looks like this. The thickness is right here. Now blood has to come here, turn around, and go back out this hole. Well, what we've done really is we've kind of put a thumb over that outflow tract, haven't we? When we do that, it increases the velocity and the pressure going through there. So we've obstructed flow partially by this area of asymmetrical septal hypertrophy. How can you treat that? Well, you can try to relax the heart by giving them medicines, beta blockers or negative inotropes, Verapamil, Norpace. Or you can do a myectomy. You can go in and do open heart surgery and you can slice out the septum. That's pretty radical. It's been done. Or you can come down the LAD and put a catheter into the septal perforator branch and inject alcohol straight into the branch. When you do that, you cause a controlled infarction of the septum. You have an MI involved in the septum. It shrinks when MI vessels, they get fibrotic and they shrink, and that muscle shrinks back up and kind of shrinks out of the way. That's called an alcohol septal ablation. That's kind of the latest therapy for HOCM. The other thing you get with hypertrophic obstructive cardiomyopathy is you get what they call SAM. So you got to know that they've got ASH and SAM. Those are the two things you really have to know. What's SAM? Systolic anterior motion of the mitral valve. Normally when the mitral valve closes, which I'm picturing right here, when the mitral valve closes, it looks kind of like this. What SAM is it looks like this. The leaflets are still closed, but they get swept over. We don't know exactly why. And when they get swept over, what happens is, instead of the valve closing like this, the valve goes like this. Why is it? So it's systolic. It happens during systoles when the heart's contracting. It's anterior. It's moving up in this motion. So it's systolic anterior motion of the mitral valve. And look what that does to the hole. There's actually been cases where one of the treatments they tried was mitral valve replacement. You just cut all that out and you put a mitral valve in there. Not a great therapy. Another therapy that's been tried that's been kind of interesting, it works about half the time. I've had a couple of remarkable cases, is you do dual chamber pacing. And nobody knows exactly why it works. There's all kinds of theories about it. Some theories are it causes premature contraction of the right ventricular wall and it pulls it away. But you have to have atrial and ventricular pacing. Sometimes when you do that, the gradients go way, way down. The problem with this disease is this is something that causes sudden death. And it can be, no warning, when you hear about these high school football players that drop dead on the football field, it's almost always this. And undiagnosed. And that's really kind of a tragic thing because this is pretty easy to pick up on a physical examination. This produces a murmur, as you might expect, because you're having a high velocity of blood going through a narrow area, and it's out the outflow tract, so it sounds kind of like aortic stenosis. It's got a lub zzz. It's an ejection murmur. But here's the trick. It's the only murmur that gets softer with squatting. Nice pearl. Now when you squat, what happens? You press all that blood in your legs and it just increases venous return. It'd be like taking inspiration. Squatting increases venous return. It means you got to pump more blood through the heart. Every other murmur, if you're going through either leaking or pushing out of the heart, when you push more blood through it, it's going to make more noise. In this case, when you put more blood in the heart, it stretches the heart a little bit and it makes the obstruction less. So this is the only murmur that gets softer with squatting. So if you're ever doing high school football physicals, really all you really should be focusing on, I'm going to listen for this murmur. If I hear a systolic murmur, you squat them, which just means you squat like a catcher in baseball with the kid. If it gets softer, they're grounded until they see a cardiologist get an echo. If they've got this, they never play again. They may get a defibrillator. This is a very dangerous thing. And you echo the relatives because this runs in families. So you can really save a lot of lives if you're tuned into this disease and you pick it up. So kind of a real quick subset of hypertrophic cardiomyopathy that is very important. Now, I like physiology. That was my major in college, so I don't know if you like physiology, but we're going to play some physiology games now. What's the definition of a compensatory mechanism? You know, the thing that bothered me about physiology is I can never tell what came first and what came second. Was it the chicken or the egg? What causes what? I always got confused about that. And part of the reason is because of compensatory mechanisms. Here's a definition. This is my definition of a compensatory mechanism. It's a physiologic response to a pathologic stimulus that in the short term is good, but in the long term is bad. Let me walk back through that again. It's a physiologic response to a pathological stimulus. In the short term is good and the long term is bad. What do we mean by that? Well, you're walking down the woods one day and a saber-toothed tiger jumps out of the woods and gores you in the belly and you're bleeding to death. That's a pathological stimulus. And so you need to have a physiologic response to that. And so what do? You constrict down all your blood vessels, except the only blood that you maintain is blood that goes to your brain and your heart, right? Everything else shuts down. That saves your life. In the short term, that's good. But if you were to live like that for another year, your fingers would fall off and your toes would fall off and your kidneys would die because they're not getting any blood. So a compensatory mechanism, it's a physiological response, a pathological mechanism. Short term is good, long term is bad. That's an example. That's what keeps soldiers alive. These guys get shot, soldiers get shot in the field. These young kids can shut things down and they can live for an hour. But you got to get them fixed in an hour or they're dead. And so that's all we do in the war zones is how fast can we get these guys mobilized and turn this stuff around, okay? One of the tricks of medicine, as you come up with plans to treat people, is to try to figure out what's the compensatory mechanism that's now hurting me and what can I do about it, okay? An example, if you have really bad left ventricular function and you can't pump any blood out of your heart to speak of, your kidneys are downstream. Now your kidneys are selfish organs. They think they should get all of the blood. And if they aren't getting blood, they're also not very bright. They think, what happened? Saber-toothed tiger must have jumped out of the woods and gored us, and that's why I'm not getting any blood, so I need to save sodium. Because I must be losing volume, so I'm just going to start saving sodium like crazy. The trouble is that what the patient with heart failure needs? It's exactly the wrong response. So how do we do that? How do we deal with that? How do we overcome that? We give them Lasix. We tell the body, kidneys, you're making a mistake. You got it all wrong. We're not bleeding to death. We're just not pumping blood to you. You need to go ahead and let go of that sodium, so we give them Lasix to do that. And that's an example of how a lot of what we do in medicine is overcoming these chronic versions of compensatory mechanisms so that we tell the body what it should be doing, not what it thinks it should be doing. And that's a lot of the basis of therapy. When the drug reps come and they give you lunch and they say, if you take this drug for high blood pressure, it will cause regression of left ventricular hypertrophy. Are they telling you the truth? Will left ventricular hypertrophy actually get better if you take blood pressure medicine? That's what they tell you. Well, it's still legal for them to lie to you. Of course it works. Now what's going on there? That's very interesting. Why do you get high blood pressure? Why do you get left ventricular hypertrophy with blood pressure? And then when you get the blood pressure down, it'll get better again. Why is it? It's because it's a compensatory mechanism. So why is left ventricular hypertrophy of benefit? We've told you that LVH and a hypertrophic cardiomyopathy over a long term is probably not a good thing for you. It can degenerate into even a worse cardiomyopathy. So unchecked LVH is not a good thing. But why might it be a good thing in the short run? Well, one of the common answers I get is because the blood pressure is elevated and the heart has to do all that extra work to pump against that high blood pressure. And it's a good answer because it makes sense, but it's the wrong answer. Your blood pressure at 150, which is elevated, will cause LVH, but you can pump to a blood pressure of 300. So you're really telling me that that little blood pressure is what causes all the LVH? No, that's not what causes it. In fact, the reason you have high blood pressure is because you're pumping blood not against high blood pressure, but through resistance vessels that are raising your pressure. So that takes us into the concept of what is afterload. I find that the discussion of preload and afterload are two of the more confusing concepts in cardiology. So we're going to walk out of here in just a few minutes and we're going to know exactly what those issues are. What's afterload? Some people tell me it's high blood pressure. Some people say no, it's SVR. Well, let's go to something called the formula of Laplace. What Laplace said is that wall stress, and sometimes in books they might be termed wall tension, and when you see that it causes a very mild variation in the formula. So let's just kind of talk about wall stress. But if you're reading this in a book and you see wall tension, think of it as the same thing as wall stress. You can pretty much think of those things as synonymous terms. Okay? Wall stress is a formula, and that is PR over 2H. Okay? Let's think of a balloon. We have a balloon here, thin little wall, and wall stress is your fear that the balloon's going to bust. I can measure that by taking a movie of you blowing a balloon up, and as you start to squint, that tells me you know the wall stress is getting to be very high because you're afraid it's about to bust in your face. More stress on the wall, the more likely it is to explode, right? It says that wall stress is proportional to the amount of pressure in the balloon. That makes sense. You put more and more pressure in the balloon, more and more stress on the walls, it's going to eventually bust, right? It also says it's proportional to the radius. Let's say we didn't put any air in the balloon, we just put our hands in the balloon and we stretched the balloon as wide as we could. It's still going to put a lot of stress on the wall of the balloon. You could tear the wall of the balloon, right? So radius will also create wall stress. Divided by 2H, what does H stand for? H is wall thickness. And in fact, it's the power of 2. So if you have a wall that's under stress, one way you can reduce the stress in that wall is to thicken the wall. And if you do, what does it do to wall stress? It lowers it because it's in the denominator. If you think about this, let's say I took 2 balloons and I had one balloon that's a little tiny, thin-walled, 1 penny birthday balloon, and you blow it up to this size, and you're kind of going, boy, I'm afraid it's going to bust. And then you get one of these real fancy $5 balloons made out of real thick rubber, and you blow it to the same size, and it's real spongy, and you say, which one has the higher wall stress? The thin-walled balloon. Why does it have a higher wall stress? Because this one has a much thicker wall, and the formula of Laplace says that wall tension or wall stress is much higher in the thin balloon. Okay? Now what's the definition of afterload? Wall stress. That's what afterload is. I'm going to be more specific with you than that. Because of the way the heart is shaped, the heart is shaped like a bullet. It's called a prolate ellipse. It's not a basketball. It's a prolate ellipse. And one of the reasons it's in that shape is that's the shape that gives you the lowest wall stress possible for the volume. And it distributes the stress on the wall in a circumferential fashion around the muscles. That's how the muscle fibers orient the wall stress. It goes around the heart. If you get a heart that's a myopathic heart and it starts to bulge, about the highest wall stress structure you can come up with is a basketball. That's why they bounce so well. They come right back to you. That's a bad wall stress. So part of what we talk about in our therapeutics, post-MI and medicines, is ventricular remodeling. We don't want ventricles to become round and basketball shaped. We want to keep them in the shape where they have low wall stresses. Okay? So the definition of afterload is circumferential wall stress. But there's even more to the definition than that. We call things preload and afterload, and nobody ever asked the question, after what? Before and after what? It is circumferential wall stress after the onset of systole. In other words, after the heart starts to contract. That's the definition of afterload. Now, if your blood pressure is up, you're having to generate much higher wall stress to generate that flow to get through those resistance vessels, your wall stress will go up. You want to lower that wall stress, you get a thick hypertrophy ventricle. Okay? We all right with that concept? Let's jump over real quick and talk about preload. Everybody remember in physiology the old frog muscle experiment where they do a hangman's thing there and they hang a piece of frog muscle there, and the frog muscle is just sitting there, it's just hanging in space, and then you zap it with a battery, put a little electrical current, and the muscle goes, zzz, it shortens up a little bit, right? Contracts. And if you do this and you plot it out on a graph, and you have, and then you take a little string and you attach a little pan and you put a weight in there so that you're stretching that muscle a little bit before you zap it. When you zap it again, it contracts even more. And you put a bigger weight in there and it contracts even more. So if you look at this as far as the weight in the pan, and this is the contraction length, something like that, and you plot that out where it's not no weight and it contracts a little bit, and then you put more weight and it contracts more, and you put more weight, you get a curve looks like that. Called Starling's curve, Frank Starling curve. That's preload. And what you're talking about is you're taking that muscle, and if you pull that muscle and stretch those fibers a little bit before you contract, it contracts more. The sarcomeres are stuck together, and you stretch them a little bit, they just contract more vigorously, up to a point, and then it kind of goes away. And maybe that's where the stretch becomes so severe that they're no longer overlapping. We're not sure about that. So that's Starling's curve. It's the relationship between stretch on the muscle and performance of the muscle. Now, in the left ventricle, how would you stretch the left ventricle before it contracts? You want to hang it from a string and put a weight on it? That doesn't seem very practical. How would you stretch it? You fill it with blood. When you fill it with blood, it stretches the heart a little bit. Okay? So when is the heart most full of blood? Well, it's filling with blood during diastole, and so it's gradually filling up, and then just before it starts to contract and empty that's the moment when it's most full of blood. That's the moment when you have the weight on the frog muscle. You have stretched that muscle and you have preloaded it, so as you have left ventricular in diastolic volume, that's preload, which correlates with left ventricular end diastolic pressure. Higher the volume, higher the pressure. We try to measure that in the body. We may call that pulmonary wedge pressure. We have a lot of ways of talking about that. And then we measure performance. And how do we measure performance of the left ventricle? Oh, there's a lot of ways of doing it. We can measure cardiac output. We can measure cardiac index. We can measure stroke volume. We can measure change in pressure over change in time. There's some measure of performance. And what it says is, as you increase the stretch, you increase the performance. That's a relationship of preload to performance. What's the definition of preload? It's not that. It's circumferential wall stress, circumferential left ventricular wall stress prior to the onset of systole. So pre and post means pre S1 or initiation of contraction and post S1 or initiation of contraction. And that's the relationship. Once you see that, what you start to realize is if you've already got a little bit of wall stress started before contraction and then it generates more wall stress to do its job, then preload is a component of afterload. It's a part of afterload. There's a test question we often ask the residents and the fellows: what does dopamine do to wedge pressure? Well, wedge pressure is a measure of preload, and we know that dopamine increases blood pressure after load. It's a pressor. And really what I'm doing when I ask that question, I'm testing the concept. Do you understand that if you increase one, you tend to increase the other one in the same direction? You may not increase it nearly to the same magnitude. So what does dopamine do? It tends to raise your wedge pressure a little bit. What do vasodilators tend to do? It tends to lower your wedge. Even if it's a pure afterload agent, it'll tend to lower the preload, but they tend to move in the same direction. It's just kind of a nice general rule to kind of remember as you're trying to pick out drugs and do I have enough wedge pressure to do this, or if I give this drug, what will happen to my wedge pressure? It's a nice little trick to let you kind of think about that so you take it in consideration and don't do something silly where you drop the wedge pressure out too low and cause hypotension. So those are the conditions of connecting up the concepts of preload and afterload. Now, let's move to a concept called Ohm's law. Everybody liked physics in high school, right? And everybody who's on the EP services deals with Ohm's law a lot. So what's the definition of Ohm's law? If you're an electrical engineer, you say E equals IR. But we're not electrical engineers, so we're going to go to the more generic, and that's V equals IR. V is what? Voltage. What's the unit of measure of voltage? Volts. I is current. Unit of current is amperes or amps. Unit of resistance is ohms. So V equals IR. I find it funny. I used to make the same mistake until I thought about this for a while. Someone would come and they'd show me an electrical device and would say this is a 5 volt and 3 amp device. I'm going 5 volts, 3 amps. It's all, I mean, amps, volts, what's the difference? You know, it's all kind of the same. I couldn't really make much sense out of that, to be quite honest. Well, let me tell you what the cardiology equivalent is to Ohm's law. We're going to put it in our language, and this is what we're going to spend the rest of the evening talking about. Pressure equals flow times resistance. Pressure is blood pressure. Flow is cardiac output. These are things that we're very comfortable with. Resistance is resistance. What's the unit for blood pressure? You take someone's blood pressure, it's millimeters of mercury, right? What's the unit of flow, cardiac output? Liters per minute. 4.3 liters per minute. Now, we would sit there, if an electrical engineer walked up to us and I said, you know, flow, pressure is the same. I think the blood pressure is 120 over 80 liters per minute. We'd say, that's the most ridiculous thing I've ever heard. That's stupid. Or they can say, the cardiac output was 4.2 millimeters of mercury. What are you talking about? That's what they think when we get volts and amps mixed up. Pressure equals flow times. This is how much pressure it takes to push a volume of fluid through a pipe of a certain diameter. Voltage is how much pressure it takes to push a flow of electrons through a wire. It's exactly the same concept. So we're going to use this one because it's something that we feel more comfortable with. Okay? Now, resistance is where all the magic is in terms of really making a big impact on your pressure. Much more powerful than flow as far as affecting your blood pressure. That's why your body regulates blood pressure by affecting the resistance in the arteriolar vessels. How much pressure does it take to get the same amount of flow out of something that has a different diameter? You know, resistance is exponentially related to diameter. Now, we all know that because if you're in the business of McDonald's and you're selling salty food because you want to sell Cokes for $1.50 that cost you a penny, then you want people buying a lot of Coke, so you give salty food. And what kind of straw would you give people in a Coke like that? A big one. In fact, if you notice, McDonald's gives you the same size straw for Coke as they do for a milkshake. So you can suck down a big Coke in a short amount of time, right? Now, let's say you go to a cocktail party and they give you a Coke in a glass that big and they charge you $5 for it. If you use the McDonald's straw and you slurped it down in 2 seconds, you'd be pretty upset, right? So what do they give you? They give you a pipette. It's going to take you 15 minutes to drink that Coke. Why? Because to get the same amount of flow with that resistance, you got to put a ton of pressure. You're sucking your guts out trying to get any pop out of there. So this is the restaurant's understanding of Ohm's law. I got home one night, I was tired, I walk in the door, my wife says, got to take John wants to go to the firehouse. I'm going, oh boy, got to go to the fire station. So we get in the car, go down to the fire station, he's a little fella, and my son wants to look at your fire trucks, so we're sitting there, and so we get to talking. And I started to get very fascinated by this because they start talking about how their problem is getting fire hose flow up to the 5th and 6th and 7th stories of buildings. And how do they do that? And so we started talking about it. And he said, well, the first thing is our hoses have to fold flat because we have to carry such a long length of hose, we can't roll them up. So they have to be cloth hoses. And that's good, but when they're cloth hoses, they can expand. And if they expand, we lose pressure. So they understood this concept of resistance. And so they have these interwoven hoses that fold flat but don't expand. very, very fancy foldable hoses. And then they have these nozzles on them so they can crimp these nozzles down and they can decrease the orifice size. It's kind of like putting your thumb over the end of the hose, really increases the pressure, right? Because pressure is flow times resistance. Same flow, turn the nozzle on at the wall, but I put my thumb over the nozzle, I get a lot more pressure out of the hose. So they can do that. But then they had another trick I didn't know about. You know, when you go to the fire, you always want to look at those big, fancy, sexy ladder trucks where the ladders can go up 5 floors and the big, giant trucks. There's a real little dumpy truck that nobody really pays the attention to. It's called a pumper truck. It's got lots of little nozzles on it. What happens with the pumper truck is you have a fire hydrant like this, a pretty bad fire hydrant, and they put the truck here, and they take a hose and hook it into the pumper truck, and there's a lot of flow that comes out of here, so they can fill the pumper truck up very fast. They fill the truck up with a lot of fluid, and then they pump that out at a faster flow rate. And so the pumper truck is designed to increase flow, and the nozzles are designed to increase resistance, and they can radically increase the pressure so much they knock the fireman down. It takes 2 or 3 guys to hold the hoses. I'm going, this is great stuff. This is exactly what we do in the heart. So it turned out to be a very good trip to the fire hydrant. You see lots of people applying these principles out in the real world, and we're going to apply them a lot as we go through our hemodynamic sections. So let's take those 3 elements, pressure, flow, and resistance, and talk about those a little bit. We'll talk about blood pressure first because it's the easiest thing to work through. We talked about pulse pressure in a previous lecture. Pulse pressure is the difference between systolic blood pressure and diastolic blood pressure, right? So that's one of the formulas we think about. What about mean arterial pressure? Anybody calculate that? I know, it's that some kind of that silly formula to see, it's 1/3 or 2/3 or something or other, right? There's a real easy formula I'm going to tell you, a much easier formula to do it. Mean arterial pressure equals diastolic blood pressure plus 1/3 of the pulse pressure. That's an easy formula to learn. Much easier than the one they always print in the textbooks. Now, why does that work? What we're trying to do is we're trying to figure out what the average blood pressure is over time. Why do we do that? Because when we do mathematics and try to calculate things using Ohm's law, we can't do numbers like 120 over 80. How do you multiply 120 over 80 by 5? There's no way of really doing that without using matrix mathematics, and we're not bright enough to do that. So we have to have a number, a single number. So we take an average blood pressure over a period of time and get a single number, and that's what we put into our formulas, okay? So why does this formula work? Well, think about this. S1, S2, S1, right? Systole, diastole. It turns out we spend about 1/3 of our time in systole and about 2/3 of our time in diastole. So let's say our blood pressure is 120 over 90. What that means is 100% of the time we have a blood pressure of at least 90, right? Because during diastole it's 90, and during systole it's even more than that. So 100% of the time we have a blood pressure of 90. So that's that. And then during systole, 1/3 of the time we have some extra pressure. And how much is that extra pressure? It's the difference between the two, which is your pulse pressure. So you add that, but that's only increased 1/3 of the time. So you take diastolic blood pressure plus the difference 1/3. So what's the mean arterial pressure of that number? 120 over 90? It's 90 plus 1/3 of 30 is 10, so the mean arterial pressure is 100. See how quick you can do it? What's the mean arterial pressure of 160 over 100? 120. Mean arterial pressure of 120 over 60? 80. Mean arterial pressure of 120 over 80? 93. That's how fast you can do the math, because it's just, there's nothing to it. And that's the reason that formula is the way it is. Okay? We're going to come back to this later on. That's why I'm spending a little time on blood pressure. Well, let's talk about resistance. You cannot measure resistance. And people always give me a puzzled look by that. But if you think you can, get your resistomometer out and let's go down the hall and measure somebody's resistance. There isn't a resistomometer, is there? We have blood pressure measurements. We have blood pressure cuffs or art lines. We can measure blood pressure directly. and we can measure flow directly, cardiac outputs, and about swans, but we can't measure resistances. So it turns out that pressure equals flow times resistance. We've got to calculate a resistance. We can't do anything else. Okay, I'm going to give you 4 formulas. I want you to pick the right one off the list. We're going to calculate SVR. Everybody got the formula for SVR memorized? Yeah, thought so. Hard formula, right? Okay, mean arterial pressure minus right atrial pressure over cardiac output times 80, or right atrial pressure minus mean arterial pressure over cardiac output times 80, or cardiac output over mean arterial pressure minus right atrial pressure times 80, or cardiac output over right atrial pressure minus mean arterial pressure times 80. That'd be a nice test question, wouldn't it? You'd sit there and go, how am I supposed to remember that? Well, you're not supposed to memorize it. That's how you're supposed to remember it. How do you solve for that? First of all, 80 is just a conversion factor, so you can ignore that. Okay, that's no difference. Well, don't forget Ohm's law, because what does Ohm's law say? Pressure equals flow times resistance. We want to solve for resistance. Resistance equals pressure over flow. Well, those two are wrong then, aren't they? Those are flows over pressure. And what's a higher number, mean arterial pressure or right atrial pressure? Mean arterial pressure is going to be 90 or 100. Right atrial pressure is going to be 5 or 10. It doesn't make sense you're going to have a negative number, is it? You can come right to this and you can figure that out. All it is Ohm's law. And I don't see anybody who ever recognizes that. They just see all this fancy formula. The reason is it's a little bit dense. There's a lot going on in the formula. So let's break that formula down and look at it for a minute and see if we can de-intensify it a little bit. And I think the interesting part of this formula, cardiac output is really great, that's flow. But what's this mean arterial pressure minus right atrial pressure? What's this MAP minus RAP stuff? Why are we doing that? And there's a concept here we're going to come back to over and over again. So let's really spend a little time talking about this. Here's a tunnel, and we're going to drive a car through the tunnel. Okay? And before we start going through the tunnel, we have 10 gallons of gas in the car. And when we get to the end of the tunnel, we have 5 gallons of gas in the car. How many gallons of gas did we use in the trip through the tunnel? 5 gallons of gas, right? Now, you could say, but really, wouldn't it be nice if this was always 5 and this was always 0? Trouble is, you'd be out of gas and you couldn't go any further. So life isn't like that. So really, if you want to know from the beginning of the circuit to the end of the circuit, how much gas did I use up traveling the circuit, all you need to know is how much you had when you started and how much you had when you ended. Okay? So let's go measure resistance in a circuit. And we're going to define this circuit as the systemic vascular resistance. What is that? It turns out there's 2 different circuits that we're talking about. We have the systemic vasculature and the pulmonic vasculature. And if you have the total vascular resistance, it's equal to the systemic vascular resistance plus the pulmonic vascular resistance. Okay? We're just talking about systemic vascular resistance. And here's the trick. I'm going to give you a definition that will make this very, very easy. You don't count the pumping chambers, which we call the ventricles. You forget about them because they're the ones that are doing the pumping to the next circuit. So eliminate the ventricles from the equation. So what's the first vascular structure in the systemic vasculature? What's the first vascular structure after the left ventricle? The aorta. Right? What's the last vascular structure before the next pumping chamber of the right ventricle? It's the right atrium. How do you measure the average pressure? Because we can't use anything but mean pressures. What's the mean pressure in the aorta. It's called the mean arterial pressure, which we just learned how to calculate. And what's the, and this is actually mean right atrial pressure. And so if we want to know how much pressure we used up to go through the systemic vasculature so we can use Ohm's law, we got to know how much we started with and how much we had when we got left over. And so this is, let's say the blood pressure is 120 over 90. So the mean arterial pressure is what, 100? And the pressure here is 10. Then how much pressure do we use up in the system? We use up 90, so it's 90 over cardiac output times 80. One of the tricks I'll do is when I walk into the unit, I'll start asking the nurse for information. And it looks kind of like a magic trick again, but what I'm doing is I'm asking for information in a sequence. And so I walk in and I say, how's the blood pressure? And the nurse says, the blood pressure is 120 over 90. And so I go, 100. I say, what's the right atrial pressure? They say it's 10. I go, 100 minus 10, 90. Okay. What's the cardiac output? And they go, it's 5. So 90 divided by 5 is 16. 16 times 80. I do the SVR in my head. And so I walk out and say, oh, well, the SVR is so much numbers. And they go, how'd you do that? Well, I didn't do it all at once, I can tell you that. I did it in little bits and bytes of pieces. So you measure the cardiac output by breaking it down, and you can figure those numbers out very, very quickly. In that case, it'd be what's 16 times 80? Well, it's 160 times 8. So I'm going 80 plus 1280. That's about 1280, 1300, right? I don't know, let me check, and they plug it all in the computer. It's 1280. Gosh, how'd you do that? It's because I just asked for the information in the sequence I wanted it so that I can walk in and do the SVR calculation. And it's all this concept of knowing the circuit. Now, with that said, let's figure out what the formula is for pulmonic vascular resistance. So PVR, I'm going to make it easy. It's divided by cardiac output times 80. Unless you want to use Wood's units, in which case you take off the 80. So what would be the answer to that? Well, let's think it through. What's the first vascular structure after the right ventricle? Pulmonary artery. But I need to have an average number, so it's mean PA pressure minus what's the last vascular structure before the left ventricle? Left atrium. And what we're going to talk about in just a moment is left atrial pressure can be measured with a swan, and it's the same thing as a pulmonary wedge pressure. So you'll see a lot of textbooks will say that it's actually PA mean minus pulmonary wedge pressure. And that's pulmonic vascular resistance. So you really should never have to remember these equations. You could just sit there for a second and think about it, go through the rules. Okay, if I'm on the pulmonary side, what's my first structure after the pumping chamber? Be PA. Okay, so mean PA minus, left atrial pressure divided by cardiac output times 80. Okay? That way resistance gets to be a whole lot easier. We're going to talk about one more concept, and then we'll dive into hemodynamic workshop so we can really work through some problems and figure out how to use these numbers a little bit more. Cardiac output. We've talked about how we measure blood pressure, which is directly, and how we calculate mean arterial pressure. We've talked about how we calculate a resistance off of those numbers, but how do we actually measure cardiac output? Imagine you had a tube, a plastic or a glass pipe, and water, distilled water just flowing through there, just this beautiful pipe with this clear water going through there. And on top of this pipe, you had a spectrophotometer which could measure changes in the penetration of light through that water. And since it's just pure water, the light just goes right on through, no obstruction, right? And upstream here, in a little valve, we inject 10 cc's of black dye right in the pot. When you do that, you kind of get this bolus. And so you get a little bit of dark stuff, then you get this big dark stuff, then it kind of dilutes out eventually. And if you plotted that out, you'd have something that looks like this, and then you get you get this curve and go back away to turn back to normal water again, right? And it turns out if you know how far upstream it was from the measuring device, and you know how much you injected. You can take that and you take the area under the curve, and that's your cardiac output, or that's your flow through the pipe. And what they used to use in the old days, they used to call it, they used to inject green dye, particularly in these kids, and they would put a pulse ox on them, and they would see how long it would take for the curve to go away, and that was called the dye dilution method. I mean, that's kind of an old historical thing, the dye dilution method. Well, we don't want to be doing that nowadays, but what if instead of being a spectrophotometer, it was a thermometer? It was just measuring the temperature of the water, and instead of injecting dye into the water, we just injected a bolus of cold water. And we knew how far upstream it was, and we knew what the temperature of the water was that we were injecting. What would happen, we would get a curve just like that, take the area into the curve, and we would be able to measure flow. And that's cardiac output using the dye dilution method? No, the thermodilution method. And so we write that oftentimes as cardiac output TD. That's all cardiac outputs are. Some places ice down the water. All you have to do is you have to have a temperature probe in the water that you're going to be injecting. You have to know what that temperature is. You can use room water, room temperature. Why room temperature? Because room temperature is going to be 72 degrees and the body's a 98.6. There's still a 28 degree difference. You have to ice it down necessarily. A lot of places do, but it's not required. So that's the thermodilution method. Well, let's talk about swans for a minute. Are swans mysterious to you sometimes? It's really an interesting story. I don't know if this is exactly true, but I'm going to make it up. I'm going to pretend like it's true. Jeremy Swan just died this last year. The Swan-Ganz catheter, that maybe should be called the Swan-Ganz Forrester catheter, after Jeremy Swan, Willie Ganz, and James Forrester. And they thought something like this: can we measure left ventricular end diastolic pressure? That's our measure of preload. Remember that? It's the pressure just before the ventricle ejects. Can we measure that directly? What if I stuck a catheter in the left ventricle and measured the left ventricular pressure? Am I measuring it? Yeah, it's whatever that is right there. Just before contraction, I'm measuring the pressure just before there. That's a real important thing, and there's just a little trick. Every time we do a heart cath, we measure that. And it's on the cath reports. Nobody ever looks at it. Well, what's the patient's wedge pressure? I don't know, but you got cath today. Maybe you ought to put a swan in. Maybe you ought to go look at the number, because we did a pressure recording right there. If the blood pressure in the aorta is 120 over 80, and the blood pressure in the left ventricle is 120 over 10, what's the 10 telling me? That's what we would call a wedge pressure with a swan. It's the left ventricular end diastolic pressure. The number may well be there, you don't even know it. So really look at the cath reports, you'll find them there sometimes. So yes, we can do that. The trouble was, I'd like to know the wedge pressure maybe several times a day over 2 or 3 days, and I can't leave a pigtail catheter in their left ventricle for 3 days. And I want to do a heart cath 12 times on them in 3 days. So wouldn't it be nice if we could measure wedge pressure, or left ventricular end diastolic pressure, from the venous side? So we put a catheter in, leave it in for a few days, and then take it out, and we could measure something on the other side. We could measure a left ventricular arterial pressure from the venous side. Now, how in the world can you do that? And that's where these guys are really, really smart. Here's how they probably worked it out. I wasn't there, but this is how I think they must have worked it out. Okay, we have the aorta, we have aortic valve, we have a left ventricle, mitral valve, a left atrium, pulmonary vein, pulmonary capillaries, pulmonary artery, pulmonic valve, right ventricle, tricuspid valve, right atrium, IVC, SVC, right? Let's work our way back up to here. What we really want to know is we really want to know what that pressure is in diastole just before contraction begins. We want to know what the preload is. That's our goal. Well, let's work our way backwards. Are we measuring something in systole or diastole? Diastole. Is the mitral valve open or closed during diastole? It's open, because blood's going from the left atrium into the left ventricle where the ventricle is resting. So during diastole, the mitral valve is open. At the end of diastole, the pressures have been pretty much equalized. So you could say if you knew left atrial pressure, you'd have a good idea of what left ventricular end diastolic pressure is. So maybe we just need to measure this instead, as long as the valve's opening in the sequence we want. But that's pretty good. They marched us back one step. What's the name of the valve between the pulmonic veins and the left atrium? There isn't one. That's good. Don't have to worry about valves then. So if we knew what the pulmonary venous pressure was, assuming there's no mitral stenosis, venous hypertension, or anything like that, if we knew what the pulmonary venous pressure was, then we would know what the left atrial pressure was, which would tell us what the left ventricular and diastolic pressure was. Well, let's back up to the pulmonary capillaries. How can we measure pressure in the pulmonary capillaries? That's a little tougher. Thankfully, Laplace tells us this thing again. He says that if you have a pressure here of X, and you have 3 channels, then the pressure is 1/3 X, 1/3 X, and 1/3 X, but it's still X. If you have 1,000,000 channels, it's 1,000,000th of X, but you don't lose pressure. It just disseminates across the bed and comes back. So we don't have to even worry about the pulmonary bed. So now we're back to the pulmonary artery. Now I'm to a structure I can reach with a catheter from the venous side. So now all I have to do is measure pulmonary artery pressure, and I now know left ventricular end diastolic pressure, right? Wrong. Because now we're screwed up by something. Where we get screwed up is we have a right ventricle that's now pumping blood into the pulmonary artery under pressure, and I'm getting pressure measurements from 2 different sides, and it messes me up. Now, when we say we have a pulmonary capillary wedge pressure, where are we measuring? Where is the balloon sitting? Sometimes people say, well, you've wedged it into the pulmonary capillaries. Nonsense. This is a big catheter. A pulmonary capillary is 10 microns. A 7-micron blood cell can hardly get through it. There's no way you're going to wedge a catheter into the pulmonary capillary. What you're doing is you take a catheter, and it comes down the SVC and the RA into the right atrium, right ventricle, and you have a balloon on it, and you blow the balloon up. And the balloon blows up right here, and here's the tip of the catheter. And this is a fluid-filled catheter. How does a fluid-filled catheter measure blood pressure? If I take a hollow catheter, and it's full of fluid, it's fluid-filled, and there's a blood pressure in this where I'm measuring, it pushes pressure on this end of the fluid column, which transmits that pressure along the fluid column. It pushes the whole column back, and I have a membrane here, like a drum, and it pushes that drum and deflects the drum, and I have a little device with a little electrode that measures how much deflection there is on the drum, and depending how much deflection there is, it tells me how much pressure there is pushing on it. So whenever you set up your transducers in the coronary care unit, you're setting up your drums that you're pushing against with your fluid-filled catheter. It turns out if you put a balloon here, the balloon isolates the end of the fluid-filled catheter from all this blood pressure coming from the right ventricle. It's shielding it. So you truly are measuring only things that are looking out ahead of you. And that was the genius of the Swan-Ganz catheter, was they figured if I wedged it in the pulmonary artery, I could measure pressure in the pulmonary capillaries, which is the same thing as everything else for it. The other nice thing about the balloon was, as it turned out, if you inflated the balloon, you could just kind of start pushing it, and it would kind of float with the flow anyway, and it would kind of naturally go out into the pulmonary artery. You could even put these in without having to have an X-ray machine to do it. Even better. So now we have a pulmonary wedge pressure. We have a measure of preload. Okay, we have a pulmonary wedge pressure, and we have a mean arterial pressure because we have a blood pressure from an art line or a blood pressure cuff. We got those 2 things right. What else can we measure here? Well, it turns out if you took a second fluid-filled catheter and you glued it to the first one and hooked it to the drum, but it was shorter than the first one, you just happened to know how far shorter it was, so that it was always in the left atrium, then you had a second catheter that would stop right here. You had a second fluid-filled, that's a right atrial, and so that's the blue port. The distal one's a yellow port. This is a blue port. So the blue port's sitting in the right atrium. So now you have a right atrial pressure. Oh, I'm starting to get some things I can measure some resistances with here, right? If only I could do a cardiac output. Well, what they did then is they said, okay, that'd be nice. We'll just put a temperature ring, we'll put a thermometer here on the tip of the ring, and we can inject through this blue port. And we actually know how much distance it is from here to the ring. We know what temperature we're going to inject. And so we can make a curve, and now we can measure cardiac output. So now we've got cardiac output using the thermal dilution method. And if you get a venous infusion port or a VIP swan, they just happen to glue another lumen on just to give you a central line. So now with the Swan-Ganz catheter, we get all kinds of tools to start doing all kinds of calculations and make some decisions. So these guys truly were pioneers as far as solving a problem and thinking their way through this. Okay, questions about that? Then let's talk about one last way to measure cardiac output in case that's wrong, because sometimes a thermal dilution cardiac output doesn't work. Why would it not work? Maybe the transducers of the drum is broken, maybe the line's clotted off, maybe the patient has TR, a lot of tricuspid regurg, so as you inject the cold water, it gets washed back, and so you're getting funny numbers. There's all kinds of reasons you can get bad numbers. So what do you do if you get a bad number? There's another way to calculate a cardiac output, and that's called a thick cardiac output. And the formula for fit cardiac output, and this is always a little complicated. Fit cardiac output equals O2 consumption divided by AV O2 difference times 10. Okay? Formula we all love. O2 consumption used to be really, really hard to measure. We could do it in the cath lab. You had to put these PUDs on them and collect expired CO2, and it was really an ordeal. It's a little easier now. We can use respiratory carts that the respiratory therapists have and metabolic carts. They can measure these. But the rule of thumb is if you just assume it's 125, that's sometimes a pretty good number for the average patient. The trouble is if they're breathing fast or they're having temperatures or they're thyrotoxic, it'll change their O2 consumption. So it's a little bit of a problem. But I want to focus on the denominator. This is where I really want to spend my time talking about this. What is AVO2 difference? Okay. AVO2 difference equals hemoglobin times arterial sat minus mixed venous O2 sat times 1.36. That's probably a formula worth memorizing. This is going to bail you out sometimes. And there's some logic to this. We'll go through this here. You are not calculating cardiac output when you do this number. You're calculating AVO2 difference. The trouble is sometimes you get a number like 4.2, which sounds like a cardiac output number. With cardiac output number, usually the higher the number, the better, the lower, the worse it is. This is exactly the opposite because it's in the denominator of the formula. The higher this number, the lower your cardiac output because you have to divide this number into O2 consumption to get cardiac output. If this number is 125 and this number is 3 times 10 is 30, 125 divided by 30 is about 4 point something, so that's how you get your cardiac output. So don't confuse this with cardiac output. If this number is less than 5, it's normal. If it's over 5, your cardiac output is low. Because this number grows, your cardiac output goes down. So this is a nice little trick. If you're in the coronary care unit and you don't have a reliable swan, you can do this calculation. You get a number of 8.2, you can go, okay, my number's down. And you can even assume it's 125 and divide it. It looks like I have a cardiac output of 1.5 or 2.2 or whatever it is. So you can do this calculation. Well, why does this work? What is he getting at here? Let me show you we're going to go to the train track, and the train track is how we always talk about this. There's a couple of rules. at any given moment, your tissues, your liver and your muscles and your brain and every organ in your body can only extract oxygen at a certain rate. Can you train your body to be more efficient over time? Yes. If you're Lance Armstrong, you can extract more oxygen than I can. But at any given moment, you are who you are, and you can just extract as much oxygen at a given. Think of it as you can have a lever reach out and grab an oxygen molecule and pull it in, and your lever can't go any faster than it is, okay? You can't suddenly double the speed of your lever. It is what it is. So think of this as a train. Here's your heart and your lungs, and there's this train track that goes around. And this is going to go all the way around the body, and it's going to come back to the heart again. And we have a train car. In fact, we have 3 train cars, let's say. And they're full of oxygen molecules, because they just came out of the lungs, right? They just went to the lung, got oxygen. The ventricle is now pumping this forward. And so now your trains start to make a trip around the track. And as it goes around the track, your kidneys and your muscles and everything, as it goes by, it reaches out and takes an oxygen molecule, and then take another one until the train goes by and it misses it and it can't take any more. And when it gets back to the train station, you still got 3 train cars. There's still some oxygen in there, but not as much, right? There's been some taken out. And what's our rule of measuring the effect of something in a circuit? We've got to know how much we started with, and we've got to know how much we ended with, and whatever the difference is between those two, that's how much we used up in the trip, right? So if we want to measure the amount of oxygen in the train cars, we would measure that with an arterial saturation. So that's arterial sat. And we want to know how much we have when we got left, and what's the most accurate measurement of blood saturation before it gets oxygenated again? It's in the last vascular structure before the lungs, which is the pulmonary artery. And we call it mixed venous because it's coming from the SVC and the IVC, and those have different concentrations a little bit. And it goes to the right atrium and the right ventricle, and it gets squished, and it's like a washing machine. When it gets out to the right ventricle, it's been mixed up. So the best place to pull a venous blood sample for SAT would be a mixed venous O2 SAT, which would be the yellow port or the distal port of the swan. And when you do that, you have a mixed venous O2 SAT. So that's how much oxygen molecules we used up in the journey. That's the AVO2 difference. Except, we need to know something else. What do the train cars represent? Hemoglobin molecules. The number of train cars is the number of hemoglobin molecules, so you get your hemoglobin level. And what's the oxygen carrying capacity of 1 gram of hemoglobin? It's one of those really trivia questions. Turns out it's 1.36. And there's your formula. Now, why is that number higher if you have a low cardiac output? Why is this number bigger? Instead of being 4, that number is 8. Well, your hemoglobin is not changing in the circuit, and that's not changing, so it must be something here. You're not raising your oxygen sat, so you must be having a lower mixed venous sat when you get back to the train station. That's what would make that number bigger, right? What would make that number bigger? If I can extract oxygen as it goes by, then it must be going by slower. So I have more time to reach out and pull oxygen off the train car. So the slower it's going, the lower the cardiac output, the more oxygen gets extracted. When you get back to the train station, you start off with an arterial sat, should be about 95%. When you get back, it should be about 70% if it's normal. You get back and it's 45%. Those trains have been going really slow, and your tissues have been just grabbing more molecules off the wagon. And that's the concept of the fit cardiac output. We were involved in a situation one night, we didn't have a swan. And we were really struggling to figure out what was going on. And so we said, okay, they had an oximeter on their finger. It said 92%, so it's 0.92. And we got a hemoglobin off the lab from that morning, and it was 10.9. We took 1.36. And I just said, just get a venous sample from their arm. It's not a mixed venous sample, but it's a venous sample. Pull a venous sample from their arm and run it through the blood gas machine real quick there in the unit. It took us about 30 seconds. We did. You get a venous sat of 45. At least we did an AVO2 difference. We said, yeah, we got a low cardiac output state. At least we knew that much without having to put a swan in. It's really a kind of a poor man's trick, but it does work. And so it's important to kind of know the concept of the fit cardiac output. It's another way besides the thermal dilution method or dye dilution method of measuring a cardiac output. And it really helps you kind of when you want to cross-check your flows. Remember, when you're doing your mixed venous and your O2 sat, those are decimal points. So when you do the formula, you don't put 92 minus 50, you put 0.92 minus 0.50. And then multiply it by 10.5 for your hemoglobin or whatever it is, and 1.36. When you do that, you should get a number that's in the 4 to 5 range. So with that, we are ready to start into our hemodynamic workshop, and we'll pass out some sheets and go through some real problem solving. Thanks.